This is the Chapter 10 Part 2 lecture video that goes over the rest of Chapter 10. Section 10.2 is on regression. This section introduces a method used for finding the equation of a straight line that best fits the points from a scatter plot. And the best fitting straight line is called either a regression line. It can also be called the regression equation, line of best fit. There's a lot of different words that we have for this. And so we can use regression equations to make predictions for values in the future with one variable given some specific for the other. So right below this, it says regression line or line of best fit or least squares line is a straight line that best fits the scatter plot of the data points. And so the regression equation that we have is going to be y equals b naught plus b1 x. And you'll notice that this looks a lot like what we saw in an algebra class with y equals mx plus b. And so we're going to have a slope and a y-intercept. And so slope is going to be our b1, and our b naught is our y-intercept. Algebraically describing the regression line, the regression equation expresses the relationship between x, and this is our exploratory variable, or our predictor variable, or independent variable, and our y is going to be called our response variable, or dependent variable. The exploratory variable is used to predict the response variable. At the top of the next page, we have calculator steps for how to find the equation of a regression line with the TI-83 or 84 calculator. So the first thing that we need to check is to make sure that all the requirements are met and satisfied, which are that our data needs to be a simple random sample, and it needs to be quantitative data. Our scatter plot needs to show an approximate linear relationship. So you would have to graph your scatter plot to look at it to determine if it looks like it could be linear. And then the last thing is that the data contains no outliers. If we have any outliers, we do need to remove those. So the next thing we're going to do is we're going to go to stat and go and input our data into L1 and L2, and then go to stat, test, and we go to F, blend reg t-test, the same thing that we've been going to this whole time for this chapter. The output gives us y equals a plus bx, where a equals the y-intercept and b is going to be equal to the slope. This is also for a TI-83, 84 graphing calculator, so if yours is using different letters for these, make sure you make a note of it and change this. But these need to be substituted into your regression equation that's given. Right below this is an example. It says the table below lists the overhead widths in centimeters of seals along with their weights in kilograms, and the study is shown right there, and you can look that up if you have any questions about it. It says to round 3 decimal places for our answers. So this one we have our overhead width and our weight, and so our overhead width is our x value and our weight is going to be our y. So first thing that we need to do is part A, which says to create a scatter plot of the data. And so I'm going to go ahead and draw my axes here. And again, remember x is the horizontal line, and that's going to be overhead width, and weight is going to go on the y. So weight, and that is given in kilograms. And the values that we have are ranging from a little bit over 100 up to about 250. So I'm going to start at 100 and just count by 50s. You can do this any way that you would like, but just make sure that all those values can fit on our graph. Likewise, for our x value, we have overhead width, with the smallest value being close to 7, and then the largest value going close up to 10. So I'm going to start this at 7, and so I'm going to have 7.5, and then 8, 8.5, and then 9, 9.5, and then 10. And labeling your axes. So check to make sure that you have both of the axes labeled. And so from here, we're just going to graph each of these seals. So the first one has 7.2 of an overhead width and a weight of 1/16. So plotting that point. The second seal is 7.4 with a weight of 154. From here, we can continue this process on and graph the other 4 seals. After plotting the values for the other 4 seals, we have our scatter plot. Again, checking to make sure you label your axes. Part B says to find the regression equation. Graph the regression equation on our scatter plot in part A. So in order to find our regression equation, we need to input in our values into our graphing calculator. X is going to go into L1 and Y is going to go into L2. We're first going to go to Stat, Edit, and then make sure we have our numbers entered into L1 and L2. Remember, your old lists that are in there you can clear by going up and highlighting L1, selecting clear, your button that says clear on it, and then scrolling down, and those numbers should automatically clear out. From here, we're going to go again to Stat, Test, and then we're going to go down to linreg t-test. From here, you need to make sure that you have your alternative hypothesis set to rho not equal to 0. You will notice that you have an A value and a B value. Round those 3 decimal places, and those 2 values are going to correspond to your slope and your y-intercept in your regression equation. Again, the slope is going to be B, and A is going to be our y-intercept. From the graphing calculator, we get y hat is equal to negative 156.879 plus 40.182 x. And you could write the 40.182x before the negative 156.879. They're both equivalent. Part B also does ask for us to have our line of best fit drawn onto our graph, so I'll make sure to do that. It is the best approximation for the line closest to those points. Part C says what is the predicted weight of a seal that has an overhead width of 9 centimeters. So this means that since our overhead width is x, that means x is equal to 9. And so we're just going to substitute this into our equation, which again was the negative 156.879 plus 40.182 times 9. Substituting this all into our calculator and working this out, we get 204.759. And again, it is asking for the weight. In weight, make sure you include your units as in kilograms. Part D says, what does the slope and the y-intercept of the regression line represent in context with the problem? So the first part we're going to talk about is the y-intercept. And in algebra, we know that this is when x is equal to 0. And so our y-intercept is when x is equal to 0, and x for us is overhead width. So when the overhead width is 0 and our units are centimeters, the weight is going to be, in what our y-intercept is that negative 156.879. And this is in kilograms. And for this problem, this does not make sense. It doesn't make sense to have a seal that has 0 for its overhead width. It would not have a head. And so for the next part, we have slope. And for slope, we know from algebra that it's rise over run, or change in y over change in x, with that delta, that symbol like a triangle, standing for change in, and called delta. It's a Greek symbol. And so for us, the change in our y variable, and y from up above is our weight, over the change in our x variable, which is overhead width. Setting this up, it allows me to explain it in words. So for this, our slope is the one that is with the x value, which is the 40.182. And since slope is always given as a fraction, so that way we can talk about both those variables, I'm just going to go ahead and put this over 1. So putting our units with it, again, weight was in kilograms, and overhead width is in centimeters. So what this says, that if overhead width increases, by 1 centimeter, that's from the denominator in that fraction, then the weight will also increase by 40.182 kilograms. And so again, looking at this, we do have 1 centimeter, which is our denominator. And so since that is a positive value, if that increases by 1 centimeter, then the weight, which is also positive, is going to increase by 40.182 kilograms. So that's interpreting our slope and our y-intercept. We have another example at the top of the next page. This example says the data in the table below gives the monthly rain totals for 2025 in Kona, Hawaii, and the corresponding number of umbrellas that are being sold for each month. So the first thing that we have is our rainfall in millimeters, it's X, and the umbrella sold, which is Y. Part A says to create a scatter plot of the data. So going ahead and drawing both as axes on my graph. The y-axis, which is umbrellas sold, I'm going to go ahead and label that. So umbrellas sold. And the value that we have, I'm going to start at 0 and just count my way up. It looks like the largest one that we have would go up to close to 50 or at 50. So 10, 20, 30, 40, 50. And then for my x-axis, the smallest value that I'm going to start at is 75, and then going on from there. Going to like 150. And for this, labeling this axis as rainfall. And this is in millimeters. So the first set of data we have set at 82 millimeters of rain and 15 umbrellas sold. So 82 and 15 umbrellas sold. So putting a point, graphing the second point, which is at 92.5 and 25 umbrellas sold. From here, we're going to continue graphing all these points that we have. After plotting all of our points, we have our scatter plot for part A. Again, make sure that you have your axes labeled. Part B says determine the linear regression equation and round 3 decimal places. From this, we need to input in x into L1 and our y values into L2 into our graphing calculator. We're first going to go to Stats, Edit, and then enter in all the values that we have for L1 and L2 into our calculator. Again, L1 is your rainfall amount in millimeters, and L2 is your umbrellas that are being sold. From here, we're going to go to Stats, go right to Test, and then scroll down until you see Lin Reg T Test. From here, you need to make sure your alternative hypothesis is set to not equals, and you'll notice that you have an A and a B value that make up your equation for your regression line, with the slope being B and your y-intercept being A. Make sure to round these 3 decimal places. From the graphing calculator, we get our regression equation as y hat equals negative 17.039 plus 0.433x. From here, part C says a large storm is expected to bring about 200 millimeters of rain. How many umbrellas should Kona, Hawaii expect to sell? And again, we're getting about 200 millimeters of rain. So that means that x is going to equal 200. From here, we're going to substitute this into our equation. And so we're going to have y hat equals negative 17.039 plus 0.433. And again, instead of x, we're going to substitute in 200. And from this, we get 69.5 0.561 by substituting that all into our graphing calculator. So this is about 70 umbrellas. Part D says to construct a formal hypothesis test. And what this means is that we need to have H0, H1, and go through and get our p-value to determine if the linear correlation exists between the monthly rainfall in millimeters and the number of umbrellas sold. And it does say use the 0.10 significance level. So for this, we're going to conduct a formal hypothesis test. We need to have H0 and H1. Since this is asking about a linear correlation, I know that we will have rho. And so our null hypothesis is that rho is going to be equal to 0, and our alternative is going to be that it's not equal to 0. And what these stand for our null is going to be no linear correlation between those two variables. And rho not equal to 0 means that there is a linear correlation. So in order to do this, because it's asking about linear correlation, we need to go to lin reg t-test on our graphing calculator. On the graphing calculator, we should already have our values in, but again, to do this, you go to Stat, Edit, and then make sure that you have all the numbers entered into L1 and L2. From here, we're going to go to Stat, Test, and then find lin reg t-test. Make sure that your alternative hypothesis is set to not equals. From here, for part B, we did get our equation of the line with A and B, those values for the regression equation. But for this one, since we are doing a hypothesis testing problem, we need our p-value. And if you look at your p-value, you'll notice that it does have that e in there, which again, remember the e stands for times 10. So this would be 1.1419 times 10 to the negative 7. From the graphing calculator, we get a p-value equal to 1.1419, and it does have that e in there, which stands for times 10 to the negative 7th. Moving that decimal point 7 times to the left and rounding 4 decimal places, this is going to equal 0.000 or just 0. And then comparing this to our alpha value, which is 0.10, we have that our p-value is less than alpha. And so what this means is we are going to reject the null hypothesis. So from here, we need to write our conclusion. So starting this off with there is sufficient evidence at the alpha equals 0.10 level of significance to conclude that, and remember, you're always supposed to discuss H1 in your conclusion, which is that there's a linear correlation. So to conclude that a linear correlation exists between, and then again, make sure you state what the problem's talking about in those two variables. So this is between monthly rainfall in millimeters and number of umbrellas sold per month. So right below this, we have what's called a residual. And a residual is the error between the predicted value and the observed value. So the residual is equal to observed value that we have for y minus the predicted y value. The criteria for determining the line of best fit describes the relationship between the two variables is based on the residuals. So we want to have the smallest amount of residual possible. The most popular technique for making the residual as small as possible is the method of least squares. And you can see that on the picture on the page at the top. And so you can see that the residuals there, those lines between the point and the line of best fit, we would like for that to be as small as possible. So to analyze the residuals, to determine whether the linear model approximates and describes the relationship between the variables, The residual plot is a scatter plot with residuals on the vertical axes and exploratory variable on the horizontal. And so right here below, there's a couple bullet points to start. So if a residual plot shows a pattern, such as a curve, then the linear model is not appropriate. And if the residual plot shows no pattern, then a linear model is appropriate. So this is another way to determine if we can use a linear regression. So to determine the value of the residual is constant. A constant error, variance, or homoscedasticity is the residual plot is spread out in an increasing pattern, and we can see that down here in the third residual plot shown. So the next section that we have is 10.3, prediction, intervals, and variations. And so in the previous section, we saw a method for using regression equations to find the predicted value y, but it would be great to have a way to determine the accuracy of such predictions. So we have a prediction interval, and so this is the range of values used to estimate a variable, such as a predictor value of y in a regression equation. We have a deviations. This is the measure of differences between the observed value and of the variable and some other value, often that of the variable's mean. The total deviations that we have are the deviations between the observed and the mean values of the response variable, and the explained deviations. This is deviations between the predicted and the mean values of the variable. And then the last one's on the top of the next page is the unexplained deviations. This is the deviations between the observed and the predicted values of the response variable. You can see all of those listed in the graph right below. And you can see your regression line, the point that we actually have of our data, the observed point, the unexpected deviations, the expected deviations, and then the total deviations. So total variations is the sum of the squares of the total deviation values. The explained variation, again, is the squares of the explained deviations, and unexplained variation is the square of the unexplained deviation values.